So in this part 2, I'm going to show how to implement the same algorithm using RTrees. And more than that, I'm going to show how RTrees also have methods to do additional spatial queries. So instead of using brute force to detect closest points or points within a certain distance, uh, the R tree is a data structure that does the spatial partition and it enables us to do these operations much more efficiently. So let's start our new code. This is the version with the R trees. And in this code, we don't need I anymore. We have a loop here inside now. We don't need to see the results of the previous code. And I'm going to bring the same inputs. So this is point. This input is points. It's a list of point for this. This is called I. And this is an integer, right? So first of all, the first step, I'm going to look for the closest point to the point 15. So I can open here. Let's import rhino.geometry srg. My R3 is in this class R3 rg.r3. I can use the dot notation and look for the functions. We are going to build a R3 here, and we're going to use in this first part here of the with the R3, we're going to use the point 3D k-neighbors. Okay, so this is the function. So we can say r equals rg.r3. This is the constructor. I'm building an instance of an AR3. Doesn't need any arguments, and I'm going to see how to use this function. So uh, this function has some arguments. It has the hay points. It has these I enumerables. They are basically data structures that are not from Python, but we are going to think about them as lists. So we can see, well, we have a list of points 3D and we have a list of points 3D. And we have an amount. So this is the amount, how many neighbors we're looking for. This is our reference point. These are the reference points, and this is like our set of points. So let's do that in our code. So our set of points is points. The second one, we are just going to use 1 point. So I'm going to create a list points I. This is a list of 1 point. And I want to look, if I look for one neighbor, we're going to be in the same position we were before. Is that, well, the closest point to this point in this set is the point itself. So I need to have like 2 neighbors. Okay. This is going to return the indices, but in a special, in a different data structure. Then it's not a Python list, so we need to convert to Python. And what I'm going to do is that let's print and understand what's this indices here, what this indices, this variable has inside. So let's say indices here. Let's print. So we are doing the query and returns R3 lazy closest point amount enumerator object. It's an enumerator, so it has like it's a collection. So let's try to convert to a list. Let's convert here. So I take this, I'll convert to a list. And we can see that this is a list containing 2 ints. Actually, it's a list containing 1 array. That the array contains 2 indices. The idea is that I only have 1 point here, right? So I could potentially have multiple points here. So I will have multiple arrays containing multiple indices. This would be the equivalent of a to-do list. So for each element of my second argument, I'll have like a respective list with the closest points. But for now, let's keep it simple. This is an array inside a Python list. We have 2 options here. I can say, let's say, let's print indices again, but now I'm going to print indices 0. And this is the array itself. And if I want to access one of these elements, I can use an index. I can say, well, I want to access the second, then I get 84. Potentially, if you want to convert this array to a list, so you're going to actually have to access a Python list, that's fine, but doesn't make any difference for our code. So let's just say that my closest point equals, it's not equal to this, this is the index of my closest point. So I can say points, indices 0, 1, and a equal points I, or let's do it better. Let's say the j, just to make it more clear. J equals this index. So we can say a equals points I and b equal points j. Okay, let's test. It's working good. Let's create b, and let's create a line between a and b. Okay, we have our line. It's working. As I move the index, I have different lines. Let's go back to 15. So this is the point in the index 84 and the point in the index 15. Now let's do for all the points. Let's see what we can do here. Potentially we can add a loop, but when we read the arguments, we notice that it accepts multiple points here. So actually, what do we do if we do just this? If we just say, well, go for each point here and look for the neighbor in the same set of points. And we're going to choose 2. But now we need to change some things. Let's comment this. We don't need this now. Let's just print. Oh, sorry. Let's just print. Let's say indices equals indices. Let's print indices actually. Print indices. Let's visualize what's happening. Again, I have a list, but now my list has multiple elements. Each of these elements is an array with the 2 values. So if you want to be organized, let's say that, let's just do a test here with list comprehension. Let's say, what if I say E for E in indices? Let's see what happens here. Okay, and what if I say E1 for E in indices? Yes. So I'm using list comprehensions to access the second element in every array that was inside my list. So I can say now that indices is equals this. So now I have a Python list with all my indices. And how can I get the point? I can say, well, closest points equal points j for j in indices. And now we can say that a equal points and b equal closest points. This is I'm just working with improvisation. Let's see if this is going to work. Okay, it's not breaking and it's working. I mean, this I doesn't make any difference now. We don't need this anymore. And we have the same algorithm. Let's see in terms of efficiency. As I move, let's start with, let's say 18. Just going to make it more sensitive to changes. As I move, let's see which one's going to be slower. You see that as I increase my input, this one starts to be really slow. I mentioned before in the previous video that this one has works is a quadratic algorithm in the sense that it works. It's a big O of n square. So in worst case scenario, you're going to run 2 loops with the n values. So you run approximately n square operations, and this one is much more efficient. So it's possible to, let's increase to 1000. This first one is going to take probably like 4 or 5 seconds. Let's see. And let me load it. Yeah, this is 5.1 seconds. This one 58 milliseconds. So this is much more efficient. So the good thing We don't need this anymore. I'm going to disable these components. And now you can see that we can visualize all these points here. All right. So this was the second part of the video, and now you know how to use the RTrees to look for closest points. And in the next part, I'm going to show how to use the method search, where you can use a sphere or a bounding box to look for points in a neighborhood. This is going to be useful for our exercises, and it's going to make our algorithms much more efficient.